we saw that in order to forecast this time series that was on the left here, we could very simply apply differencing filters at lag 1 and 16, because it's periodic of period 16. And those are the point predictions we would obtain. And those are the prediction intervals. This is what we saw last week, right? Or not? Yes, sounds familiar. What we will now see today is, if we compare the two model fitting approach, we see that this is providing a good point forecast without using parameters fitting, because essentially here we have not fitted any continuous parameters of the model. We just apply differencing filters. So you decide about the lag. The lag 16 is given by the nature of the data. So there is really no fitting performed here, and that gives fairly good point forecast, but the prediction intervals are perhaps overly pessimistic. So that's the very first thing. Did we? Sorry, yes, we saw this. What we will see now is one of the several techniques that exist to improve the forecast here. The reason why this forecast interval is not very good is because it ignores the correlation between the residuals. So differencing the data is a good idea. That will remove the seasonality, the periodic components. It will remove trends, so that will make the data look more like noise, but it will be colored noise. It will not be white noise. So the noise has some autocorrelation. Lack of independence. We spoke of it many times at the beginning of the course. Lack of independence means there is some cross-information from one residue, one epsilon, to the next. Right? If they are positively correlated, that means if an epsilon is large, the next one is likely to also be large. If they are negatively correlated, that's the other way around. So the correlation can be used for a forecast. If we have some idea of the correlation, if we know it's positive, then we can improve the forecast. Whenever we have observed that the previous residual was, which is in average 0, but by accident it was large, then we can assume the next one will also be large. So we can capture this, and that is what is done with one technique called ARMA models, or linear time series models. Everything I've done in this course is very general to any method used for forecast, whether you use machine learning methods or any kind of clustering, neural network, whatever. Everything we said so far applies to such methods. Now we dive into, this is one very specific method called a linear time series method, which is not necessarily the best for all time series models, but is one where we can very quickly go through it. The goal here is to model, to say something about a noise that appears to be stationary, but not IED here. Like perhaps this noise here. Although here it's not very clear whether it's stationary or IED. It looks like noise, that's the only thing we can see here. How can we see whether something is IED? Well, there are multiple methods. We'll see tests in next week. There's another one which is based on autocorrelation function, sample autocorrelation function. The terminology is not the same in all documents. Whether you read a signal processing document or a statistics document, they don't use exactly the same terminology. So I'm using the statistics terminology. The autocovariance function is the sample autocovariance. So that's the inner product of the signal or the time series deducted from the mean. X bar is the sample. I have a long time series. I compute X bar. I remove X bar. I obtain a time series that has 0 mean. Then I do the thing which is called in sometimes autocorrelation, but in statistics it's called the autocovariance. Right? It is square of the units of the things that we measure. It's not unit free. Then if we rescale by the gamma 0, we obtain something that's unit free, and it's called the autocorrelation function. Gamma 0 is something that we have seen already. Gamma 0 is an estimate is the maximum likelihood estimate of sigma square. So it's the one estimate of the variance. So if what we measure is bits, for example, this is in bit square, like gamma t. So this is unitless. And by the Cauchy-Schwarz inequality, it is bit, and this will tell us whether the time series appears to be stationary, right? Because if, so at least a weak form of stationarity, if it is IID, which means it's truly non-correlated, we can think of those as noisy estimates of a true unknown parameter. That would be the true the theoretical autocorrelation function, where we replace sigma by expectations. If the time series is truly IID, they're all zero. All the rho t's are zero, except the first one, rho 0, which is the common variance of all the x. But if xt plus s is independent of xs, and if x bar is truly the mean, which is non-random, then those things are independent, and the expectation of 2 will be the product of the two expectations, which will give me 0, because the expectation of this is equal to mu. Of course, in reality, we're not computing the theoretical values, but one obtained from the samples. Therefore, it will not be exactly 0, but we know something that can be used. We know a confidence interval, approximate confidence interval, that are given by, with 95% confidence, it is plus or minus 1 over square root of n, where n is the size of the sample. So that is something that is classically plotted by autocorrelation function. I did it here. For example, the original time series I had, I plotted the autocorrelation function, and the plot also plots as dotted lines the plus or minus 196 over square root of n. If the data is IID, then all the bars here, or 95% of the bars, should be between the two dotted lines, which obviously is not occurring here. And is here so what can we see about this time series? It's periodic, right? So what I did here is I computed the autocorrelation function for something that's periodic. Periodic means it's not stationary, although it's a weak form of non-stationarity. It's one that's easy to handle. It's not stationary in the sense that if there is a period, for example, here we know at this point in time we are more likely to have a large value. So there is some information from the time index t that allows us to predict something of the data. Something that is stationary means it's the same everywhere, regardless of the time. It's a subtle thing. Here, stationarity means a deterministic. Non-stationarity means there is something deterministic in the data. Now, what am I doing here? I took the red data point and I computed the autocorrelation function. And I have something that is the sample autocorrelation function, but should not be interpreted as an estimate of some statistical parameter of the time series, because the time series is obviously non-stationary. So I should make it stationary first by applying, for example, delta 16, which I did here, also delta 1. So that is not a meaningful estimate of the autocorrelation coefficients. It may be meaningful to detect stationarity if you don't see it otherwise, but it's not really estimating the theoretical coefficients. Here I have something that is more likely to appear to be stationary. Therefore, I might more likely compute the autocorrelation function. And indeed, most coefficients are very small, except at least one that is very large here, which is at lag 16. So clearly, in this time series, there is an autocorrelation at lag 16. What does it mean for you? Yes?
Elements with a difference of 16 are correlated.
Yes. And why 16?
The time series is periodic.
Yes, it's periodic of period 16. There's an autocorrelation at lag 16. That means 16 is 1 day. That means the days are not independent. When there is something not in average on 1 day, it's more likely that the next day there is something, in fact it's negatively correlated. So something away from average, but in the opposite direction. This is what this time series is showing. Why? We don't know, but this is not the goal here. We're just doing a black box approach. In some other chapters, we can discuss a non-black box approach. Negative correlations sometimes have to do with shifting things. If something has been shifted away from one day to the next day, for example, you see less traffic on this day and more on the following day. Therefore, there is a negative correlation. That is one of the recipes for negative correlations. Positive correlations are more frequent. Positive correlation means this is a busy day because it's a busy week, therefore the next day will also be busy. So if there's more traffic now, it is more likely that the next day will have more also. Positive correlations are very frequent, but here we find a time series, which is a true one, where there is negative correlation. So this negative correlation, that is clearly much larger than the error bars, means that this is not really an IID sequence, right? It has some positive correlation, which is good news. With ARMA modeling, we can capture this autocorrelation to find better forecasts. As I said, there are multiple ways to capture the autocorrelation. What we have discussed so far is only how we visualize the fact that something is not IID. Now we will model it. So one classical way of modeling it is with what is called an ARMA process. An ARMA process is defined formally in this way. An ARMA process is a stochastic process indexed by time t. T is discrete, so it just means a sequence of random variables that satisfy the following construction property. There is an inequality here that relates the x to some noise terms, where epsilon are noise terms which are IID, classically from the Gaussian distribution, but could be also something else. And here I'm assuming that the x is zero mean, otherwise if it's not zero mean, I would apply the definition to x minus mu. So this inequality, we recognize an input-output formulation that we have seen in filters already. In filter form, in compact form, I can write it exactly in this way. X is the vector of x1, x2, etc., xt. Here I'm not specifying the length. In theory, it could be infinite. Ignore mu, take mu equal to 0. X is equal to f times epsilon, where epsilon is a sequence of noises, where f is the ARMA filter with numerator polynomial 1 plus a1, b plus etc. plus ab. So denominator, sorry. So f is this filter, where b, remember, is the backshift operator. So this is an ARMA process. Of course, you have all the variants of ARMA process. If the denominator polynomial doesn't exist, we have a moving average process. If the numerator polynomial doesn't exist, we have an autoregressive process. Their interest is that with a relatively small number of parameters, we have something that, because it introduces feedback, there will be some correlation between the x. The epsilons are non-correlated, but we see that the x uses the previous x's, so they obviously introduce some feedback. So that's one way to introduce correlation. In practice, for this to be useful, we need, of course, the filters to be usable filters, stable. So in practice, we will require that the filter that's defined the f before is stable. Otherwise, I could have something that would take arbitrary values. But also that its inverse is stable. That the inverse is stable is something we require for the model to be identifiable. If I have only x, I see only something, I assume x is obtained by a simulator that has produced some epsilon and applied a filter to it. But the epsilon I will never see. They are just in my head. They are mental construction. In order to identify the epsilon, be able to compute them or estimate them, I will obtain them by the reverse filter. If the reverse filter is unstable, the epsilons will never be attainable in practice. So this method will not be useful. Here are 3 examples of ARMA processes. How did I obtain them? Well, it's very simple. I obtained the epsilon by calling a random number generator for Gaussian noise. That's very easy to do in MATLAB or Python. And then I apply the filter. Here I applied this filter, 1 minus 0.4 plus 0.95, etc. I applied the different filters that are given here. So, for example, this is this one. And I obtain here a sample in blue of this thing. Right. So this is a noise process. It has zero mean. And we see that it appears to be periodic. Right? It appears to be periodic, but as we will see, it can be made stationary, in fact. So where's the trick between something that's stationary and periodic? Here, the periods are random. So it seems to blow up, and then it decreases, and it blows up. And the average time you will spend here is always of the same order of magnitude, but it's random. So it's not something periodic. It's something that has quasi-periodic behavior, if you want, but is not strictly periodic. That's the beauty of those things, to be able to produce something that reproduces those kinds of things that are apparently periodic, but are not due to the night or the day, but are due to accumulation of randomness. For example, which of those simulations will produce what we can call a valid ARMA filter? We have a tie. A is certainly accepted. Now for B, there is some doubt. What is the question? Well, the question is very simple. An ARMA filter is, you take noise, random noise, IID noise, you apply a filter to it. This is true for both. Both of them produce a filter which is F applied to epsilon. The only thing we need to verify is whether the stability applies for the filter and its inverse. So we compute the roots of the numerator and denominator polynomials. We obtain minus 0.4 and 0.4 for f and for f minus 1. Of course, the question is the same for f and f minus 1. It needs to be stable in both directions. So both are valid ARMA processes. If we simulate them, we will see something probably very close to one of the things I've showed before. If you would simulate an f epsilon where f is unstable, you will see that the noise somewhere, after a small number of time steps, will explode somewhere. So that is not very interesting. We need to say a few things in theory about those processes. So they're very easy to construct. You take an ID sequence, so that's the simplest sequence we can build. You apply them into a filter, and you obtain something that is much richer. The analysis of this is, in fact, not so easy. I will summarize what is the findings of this here. Well, first, because if I look at what xt is as a function of epsilon, I can write something like this, where h is the impulse response of the filter. You see, that's one of the representations of a filter. So it means that xt is a linear transformation of a Gaussian IID sequence. Therefore, it's a Gaussian vector. Gaussian vectors can be defined in this way. There are other ways to define it, but one way to define them, they are linear transformations of IID sequence. Gaussian vectors have lots of nice properties. Which properties in particular? Any clue? Have you encountered already a Gaussian vector in your private life? So a random vector is something like the time series we have, x1, x2, xn. Gaussian means certainly that every x1, x2, etc. has a Gaussian distribution. But, although it's hard to imagine, but it's easy to understand that the fact that every coordinate has a Gaussian distribution doesn't mean really a lot about the process itself. Because we know, for example, if I take a vector x1, x2, saying that x1 is Gaussian and x2 is Gaussian doesn't mean much about the vector x1, x2 itself. What we don't know when I say those two things is what is the joint distribution of x1 and x2. So there is a lot of information in the joint distribution. When they are independent, there's no information. This is the easy case. If they are related, if they are not independent, if they are dependent, the joint information might be anything. If they are independent, and if the distributions of every coordinate is Gaussian, the vector is called Gaussian. In general, that's not sufficient. You can construct bizarre things where each coordinate is Gaussian, but the joint thing is very, very complicated. It's an arbitrary thing that we cannot even work with. The good things, the one that we can work with, is the one such that if you take any linear transformation of the coordinates, you obtain something that is always a Gaussian vector. That's the property of Gaussian vectors. Another property is that the distribution of a Gaussian vector is entirely defined by its means and its covariance matrix, which is not true for other general distributions. So the Gaussian vectors are the ones that are entirely defined by their first and second moments. Third moment, fourth moment, etc. don't play a role. Therefore, they are very often used. But as we've discussed already, there are things that are not Gaussian in life. So a normal process is Gaussian. That's the first thing we will see, at least the way we've defined it here. Now, because it's Gaussian, we can compute its covariance because it tells us everything about the process here. And by straightforward math, we obtain this. The covariance of xt and xt plus s is this thing here. Is xt a stationary process? Well, strictly speaking, no. Because what did we do? We took an epsilon sequence, we applied the filter. The very first output are probably not the same as the ones after we've run for a long time. And that's visible in the covariance. The covariance of x1 and x11 is given by this series, sum from j equals 0 to 10 of the cross products here. Right. So strictly speaking, it is not stationary. But we use it as a stationary process because of the following trick. The processes that we use have the property that their h here doesn't grow to infinity. So this time series, this sequence here, will be close to that, and hopefully the convergence is exponentially fast, so we'll be close to this thing here. In fact, if we require for a normal process that all the poles are modules strictly less than 1, that means that the coefficients h, as I've discussed already last week, decay exponentially fast to 0. Of course, exponentially fast doesn't say what is the exponential at with a decrease. If it's 0.999999, of course, that's a border case. But in practice, that means that those h, they decay to 0 exponentially. So we're not talking of a series in 1 over n power 1003 or something like this. We're talking of a series with respect to the exponent t, not n, which is exponential minus alpha t. Right. So that decays very fast to 0, which means even for small values of t, this is practically equal to this quantity, which is now independent of t. Right. So first take-home message, for a normal process that is well behaved, so that satisfies truly the restriction on the stability of the Arma process, of the filter. The covariance of xt and xt plus s, as soon as t is not very small, remains the same, which can be used to prove that in fact it is stationary. So it's not something that is stationary, it's something that is asymptotically stationary. But that's what we do with practically every simulation. When we simulate something, we have to remove the transients. So the same thing will happen here with Arma processes. In particular, if I look at what is the variance of xt, which is the autocovariance of xt and xt, we obtain this thing here, which is sigma squared. Sigma is the variance of the noise of the epsilon term times the series over the square of the impulse response here. first term of the impulse response is typically 1, right? If we take well-behaved, if we impose that the first response is 1, then we'll see that this is always larger than sigma squared. That's an important detail. It means that we create a noise model, the X, that may have a variance that may be much, much larger than the variance of the epsilon. Epsilon are the true residuals. But the variability, if we look at just one value, the variability may be very large. But in fact, if we filter it out and obtain the epsilon have much less variability. That's the trick of using this for modeling noise, because we will construct true residuals, or residuals that we think are better, that have much less variability. So they capture a lot of the deterministic component. We've removed some of the apparent variability. Another way to put it is that the variability of xt will be largely predictable by what we have seen of the previous x, because the time series will be autocorrelated. And this prediction is exactly what we want to do. Here I computed the autocovariance, the autocorrelation, so those coefficients that I just showed a minute ago, here, those covariance, divided by the covariance, the variance. And they are important. They show some things that are important. So on the left is what is called the autocovariance. Strictly speaking, what I said is on the left here. An interesting thing is this one here. This is a moving average process, this one here. What do we see? Well, first we see on all the terms what I predicted, that is that the terms decay exponentially fast to 0. It looks like an exponential decrease, right? But here we see more. We see it is strictly 0, except the first two terms. The first term is always 1, because I've taken the first term is the variance divided by the variance, so it's always 1. The only question is what are the next two terms? We see the next two terms are, of course, non-zero, but terms 3 and beyond are 0. Can you make sense of that? Is that just by accident for those values, or could you make sense of that? For example, if I look at the third term, right? The third term is the covariance between xt plus 3 and xt. Right? xt is this. Right? xt plus 3 is a linear combination of epsilon t plus 3, epsilon t plus 2, and epsilon t plus 1. So xt plus 3 is a linear combination of some epsilons that have a 0 intersection with the epsilons that are in the formula for xt. So they are both linear combinations of two families of epsilons that are independent of each other. So they are linear combinations of things that are independent, so they are independent of each other. So this is true because we have a moving average process. So in general, for a moving average process, the autocorrelation is exactly 0 after the number of coefficients that are given here. Why do I say that? Well, this is a way to have a hint for how to model a process. If you model a process, if you compute those coefficients, we saw how to compute them. For example, here for this time series, I computed them. So if you find something like after some order, the coefficients appear to be very small or negligible, perhaps they're never exactly 0, but if they appear to be very small after some order, then it means a moving average model might be appropriate. That is one of the use of that kind of diagram. For an autoregressive process, we see that does not occur. For an autoregressive process, it's very easy to compute the autocorrelation and from this formula, and we find them in closed form, and we'll find that they decay exponentially. For a general process, it doesn't look very different. Here on the right, I'm showing something else which is called the partial autocorrelation function. Did any of you already use that? No. So the partial autocorrelation function is defined as the residual correlation of xt plus s and xt given xt plus 1, xt plus s minus 1. So what does that mean? For example, for this process here, we see that there is dependence, there is a correlation between xt and xt plus h for every h. So between xt and xt plus 100, there is some positive or negative correlation depending on whether we are odd or even increments here. But one question might ask is there correlation because there's correlation at lag 1? If xt plus 1 depends on xt, like is obviously for an autoregressive process, xt depends on xt minus 1 and xt minus 2. Therefore, whatever you saw at xt minus 1 and xt minus 2 will influence xt. Therefore, it will also, and recursively, we can do a chain of dependencies. So it's quite normal that whatever you do here will have an impact many, many hops away. Of course, the impact decays exponentially over time because we have numbers that make the filter stable. But there is an impact that decays over time. Okay. This is so. But the question we would like to ask is, does xt plus 10 depend on x1 when we know all the values in between? So I ask the question, if I'm not asking does xt depend on x1, the answer is yes. But if I reveal x2, x9, and I take them as given, and I compute everything now conditionally to the value of x2, x9, what is the dependent? Is x1 independent of x10? Right? And since we're talking of Gaussian process, this is equivalent to computing correlation here. This is captured by the partial autocorrelation function. It would be too long to say how we can compute it, but that's a classical exercise on Gaussian vectors. It uses matrix computations, the Schur complement of a matrix. But it can be computed, and MATLAB computes it. And then here we see, as expected, that for an autoregressive process of order 2, x3 is, in the sense of this partial correlation, doesn't depend, or xt plus 3 doesn't depend on xt when we give the values of xt plus 1 and xt plus 2. Right? Because of this formula here, right? If all those values are given, then xt plus 1 will be just noise. If I treat those values as given, for example, xt minus 1, xt minus 2 are given, then xt is equal just to epsilon t plus something that is given once I've revealed those values. And epsilon t is independent of all the epsilon t minus 10, for example. So an autoregressive process has 0 partial autocorrelation at lags that are larger than the order of the process. That's another thing that can be used to decide to model things with autoregressive. Autoregressive are very commonly used because they include feedback, so there are very simple ways with very few parameters to introduce autocorrelation into the system. So those are the two take-home messages. Now, if we know how the partial and normal how the autocorrelation and partial autocorrelation look for ARMA processes, we can use this information, at least visually first, using tools otherwise, to have an idea what kind of models we could use for our noise process here. So that was for ARMA process, right? The real thing that is done most of the time is called ARIMA process, with an I. The I here, ARIMA means integrated. So that's a way the statisticians are playing with acronyms. The only thing is really to understand an ARIMA process is something that is equal to a filter applied to an ARMA process, where a filter is one like we have used. A filter that is a combination of differencing and deseasonalizing filters. What is so special about those L filters, those differencing filter, for example, it is not stable. It is just at the boundary of stability. One is an eigenvalue, is a pole of the system. So it is not stable, so we have to be careful when you use them. But it's also not catastrophically unstable, because we integrate. The reverse is the integration, and integration can be done, the reverse. But when we take the inverse filter, all the coefficients are equal to 1, for example, or even to, in some cases, values that may be non-bounded. So we still need to be careful, but in practice they are very useful because, as we have seen, they remove trends and they remove seasonal components. So, to make a long story short, an ARIMA process is simply equal to an ARMA process filtered by L. An ARMA process is a noise filtered by F, so an ARIMA process is a noise filtered by L times F. Right. So, not so... What is different about an ARIMA process versus an ARMA process, and why they have a different noise, is that an ARIMA process is not stationary, typically. Right. An ARMA process, we can think of it as stationary if we remove the transients, so it can be used to model stationary noise. An ARIMA process is not, because we have applied a filter that is essentially not reversible and will not give the time series that I mentioned before will diverge. They go to infinity. So an ARIMA process is not stationary, and we have to be aware of that when we use it for modeling here. Now, what I will do, I will apply to the noise model that we had here, this one here. I will try to fit it with ARMA, or even better, ARIMA. So in fact, since X is L applied to Y, what I will do is try to fit X as ARMA noise. And if saying X is ARMA noise, it will be the same as saying that Y is equal to X is an ARIMA process. Right? So once we think about filters, it's very simple, right? ARIMA means something like Y, ARMA something like S. So ARMA is typically for a noise process once I have removed all non-stationarity. My time series is perhaps non-stationary because it might have a trend, for it might be increasing. Also, it has a periodic behavior with a known period. So it's not something stationary. I remove all stationarity. Of course, the process I have is non-stationary. So how do we do that concretely? Well, we apply differencing filters until it appears stationary. This is what we've done on the example. And then we need to fit X, which is now a candidate to be fitted by a stationary process, to an ARMA model. Now, the good news or the bad news is this is a difficult problem. At least numeric, it's not something we do with writing a big matrix and inverting it. It is a non-convex optimization problem to solve the maximum likelihood. We've seen that fitting something that has Gaussian noise is equivalent to a least square problem. If the model is linear, then it is simply a projection. We have a big matrix formula. But here the model is linear with we call it a linear time series, but the dependency on the parameters is non-linear. What are the parameters that we're trying to fit? The coefficients, yeah. So those are the coefficients, the numerator and denominator polynomial. So it's not linear with respect to the coefficient. We call it a linear time series model because it's linear with respect to epsilon. We transform some noise, which is ID, by linear transformations. But the coefficients of the linear transformation themselves are nonlinear. So when we fit an ARMA process, it's a nonlinear and even non-convex optimization problems. But if the time series is reasonably modeled by an ARMA process, we know by general theory of statistics that maximum likelihood, when the information that there is in the time series, when the size of the sample is very large, converges, the maximum likelihood estimator converges with some sense we can make to converge in probability to the true value. So it's a nonlinear, non-convex problem, but it's not a bad one if our model is a good one. Of course, if we have 10 data points and we're trying to fit an ARMA model, it's going to be a very hard problem. If we have a large time series and the model is a good fit, or it's reasonable to assume that it comes from this model, if we plot according to some coordinate the maximum likelihood, there will be a big peak somewhere. So the problem will not be practically very hard. For MATLAB or Python to solve the maximum likelihood of an ARMA process, we typically use an iterative gradient descent algorithm, improved by some other heuristic. But the key thing to know is that we need to, any non-convex optimizer needs a best guess. If you start from flat guess, no information, it might have a hard time. Even though there is a obvious maximum somewhere, if you don't or give a hint to the optimizer, it might not find it, or it might be stuck in the local minimum or something. So the common practice when you use an ARMA process is to start with a best guess here. What are the best guess that we can do? Well, we can fit, for example, an autoregressive model. Fitting an autoregressive model is easy, and there are simple techniques for doing that are essentially trying to fit, to do what I suggested visually. What did I do visually in the past slides? I show you the exact autocorrelation function of an ARMA process. Then one trick can be, instead of computing the maximum likelihood, I can say, let me find the ARMA process that has exactly the same autocorrelation function. Does that entirely define the ARMA process? Almost. We need, in addition, the sigma square, because the autocorrelation are unit free. We need the sigma square. That will be easy to get from the scale of the process. And if there is no mean, if we have a zero mean process, that's all. There is no other parameter. So in practice, this is how we do it. We first ask MATLAB to fit an autoregressive process by doing not maximum likelihood, but what is called moment fitting. We fit a process that has the same variance as the autocovariance we measured. That's one way to fit a stochastic model. It's not the good way usually. The good way is a maximum likelihood. We know maximum likelihood when we have a lot of information. It will give us something close to the true parameters. The moment is polluted by lots of things, like if we have one outlier, the moment is very large and things like this. So, but it will give us a guess that can be used for finding a more accurate model here. So this is what I did for this thing here. So I could fit, and I say, well, it looks like, so one of the questions that we need to ask is, what is the order of the parameter? What is the P and Q? Should I find a polynomial of degree 200 or degree 2? Degree 2 would be better. We have a sparse model. But here, obviously, if I take degree 2, I will not be able to explain why there is a sudden peak at 16. Right. So what I did here is I allowed a few coefficients at order around 0 and around 16 here by asking MATLAB to force zeros here. We can do that easily. It's simply additional constraints in the optimizer. And I obtained a model that has this ACF. So I obtained some coefficients, and here is the residual I obtained. So on the residuals, they don't look very different from what I had before. But if I look at the autocorrelation function, I see that I almost succeeded. The autocorrelation function, if you remember the previous one, there was a huge peak at 16, right, which is here. So of course now I'm zooming on this region here because MATLAB adapts the Y scale automatically to my data. So in fact, it means those values are very small here. Those are the error bars, the blue dotted lines here. You could say, but not quite. But in practice, it's very hard to obtain a perfect fit. And if your data fits exactly a model, probably the data is artificial. Right? If you have real data, that never fits a simple model. But here we see that the fit is fairly good. What we could criticize, the autocorrelation seems to be okay. We could criticize something else. I would criticize something else here. Here, yeah. Exactly. The residuals seem to have a heavier tail than Gaussian. So the residuals, if my modeling is correct, those autocorrelations should be negligible with respect to the bars, which is almost true here. And this should be a Gaussian RID sequence. Obviously, there are some values that are large, that are too large for such a short RID sequence. So it is probably something that is not Gaussian, but close to non-correlated here. Right. We'll see how to handle that in a second, but we managed to do one thing, which is to remove the correlation here. Then I applied the filter, the forecasting here. How can we compute the forecast? Well, it's exactly the same as we saw last week. We have applied a differencing filter. In fact, what we saw last week was the most difficult case because L, we had to invert L and we were just at the boundary of stability and we saw how to do it. Here, my Y is equal to L minus 1X, which is L minus 1F epsilon, right? Where F is the filter of the ARMA process and L is the differencing filter. Therefore, by recursively taking the formulas of the filter, we can do the forecast given that we know how to forecast epsilon. Right? The forecast of epsilon t plus 1, having observed everything up to epsilon t, is 0, because it's zero mean independent noise sequence. Here is what we obtain. This is the forecast in red line. This is the prediction interval. And this is, here I'm recalling what we did last week when we assumed that X was RID Gaussian. Here what do we see? Well, we see there is a small difference in the forecast itself, right? The forecast here is following the data, in fact, better. And the prediction interval is smaller, which is what we expect. We expect the prediction interval to be much smaller because now we explain the variability by the variability of the epsilon, which has smaller variance. So if we do the math right, somehow this should translate into a smaller prediction interval. What we see also is a small side effect that even the prediction itself is a bit different. The red line is the prediction. And in fact, this is because now we have autocorrelation, non-zero autocorrelation in the noise. So if for some reason the value was larger at some point, then for the next point, we can exploit that to find a better prediction here. Here, the prediction is done assuming all the values up to time 224. So the deviation of the last values from their nominal or theoretical values is translated by the autocorrelation into some better prediction here. Of course, the longer we go into the future, the less this improvement shows up. So here the improvement is essentially, we see that the very first predictions are much better than if we assume they're RID Gaussian. So it's magical, right? If we exploit correlation, so a noise that is not RID, in fact, is good news. It's bad news usually for modeling, because we don't like it, we assume, we ignore it. But for prediction, it's good news. If there is correlation, there is information in the samples. How we... So, oh, sorry, did we... No. So for this, yes, we use the same formulas as we saw last week. Now, as we discussed a minute ago, as you observed, this might be a bit stretched to see this is Gaussian. So if we really want to be exploiting that information, we could do a bit better. What do we expect to be the impact of this? Which parameter will be wrongly estimated when we have this? Well, if I say this is Gaussian, this is my epsilon, in fact, right? So if I take the expected square, so the mean of those squares of this, it will be somehow an estimate of my sigma square. Right? The confidence in the prediction interval I'm doing, they're all proportional to sigma. Right? So my sigma here is probably larger than it is in reality because I have a few very large values. So the only way I can explain those very large values is with a very large sigma. A Gaussian random variable that has such a large value is very likely to have a huge sigma. Or one way to say it, if I take the sum of all those value squares, the few very large value will mean a very large. So in reality, we probably have a distribution that has a variance that is smaller, but has a tail that is heavier. So that might, for example, it might be Laplace noise, more likely here. So I could do, this exists, I could do a theory of ARMA processes with Laplace noise. Right? Everything we said, verbatim remains the same, filter things, and then we can do, fitting is a bit more difficult, but one easy thing we can do, if I don't want to reconsider my fitting, if I say, okay, this is a reasonable noise model because of this. It's reasonably IID, but non-Gaussian. If I want now to say more about a prediction, I can do bootstrap. Bootstrap from residuals, where I say, I will treat these residuals as my bag of residuals, my IID sequence. This is here. And then to say something about the future, I will perform simulations drawn from this bag of residuals with a fitted model. It gives this algorithm here. I have my data, I filter, I compute the residuals. Of course, this is after doing the fitting exercise, right? So on the examinations of the order, etc. I compute the residuals, right? When doing that, we need to be careful that our filters are assuming that whenever data is missing, it is set to 0. For example, when I do a difference, the first element of the difference is garbage. So it should be thrown away when I do this re-estimation from the noise model. So which is what I did in all the plots I've shown. I've removed the first elements that are polluted by differencing filters that are taking values of 0. This is where signal processing kicks in again. At the end, we do a simplifying assumption, but we need to be aware of it. So once I have that, I have an estimate of my residuals, and then I do Monte Carlo simulation. I do capital R replay experiment where I draw this, I replace my simulator by simply drawing from this sequence of things here, right? So I draw L numbers with respect for this, I call them epsilon here, right? And I want to predict the future. So what the past, I keep them as they are. Up to time t, this is what I have observed. And I want to simulate the future from time t plus 1 to t plus L. So I simulate in the epsilon world, I epsilon by drawing from the residuals. Then I apply the filters. I apply the filter F, and I apply the inverse of the filter L, and we need to be careful how we do it because the inverse filter is unstable. And at the end, I obtain a simulation of the future, which is yt plus L done capital R times. And then once I've simulated 999 possible outcomes of yt plus L, I take a prediction interval by doing a coverage interval, as we did usually. I did that here You can also do that for the point estimate. That will give you a coverage interval. Here I did not do it for the point estimate. I kept the point estimate unchanged, but I could also take the median of those to find a point estimate. What do we see? Well, we see a slight reduction of the prediction interval. And in fact, we see that the prediction interval is a 95 prediction interval, and I have here 25 points, 95%, so there should be, in average, there's out of the, here I have 25 points, so there should be, in average, how many? 1 out of 20, so there should be 1 or 2 points that are outside the prediction interval, right? If they are outside, that means for a true prediction interval, in average, there should be those. And here we see the prediction interval are probably too large. Here we see they're better, at least there are one point that's slightly outside, another one that touches it. So, which corresponds to the intuition that by assuming the noise was Gaussian, we were exaggerating. So that is probably the best we can do with this method to find a prediction interval. So the prediction interval is, of course, increasing over time, and but here we reduce it. In the lab, we will ask you to forecast the power consumption of EPFL over a time series that we have from the past, and then we will ask you to give a prediction interval, and the winner will be those that have the best score for the prediction. We will use a scoring function that is described in the lab homework. If I give you a prediction interval, we will interpret the prediction interval as a Gaussian distribution, where the width of your prediction interval, we take it as 2 times sigma, 196 times 2 times sigma. So we will get the sigma from the width of your interval. The mid value will give us the predicted value. So we will interpret your prediction as a distribution on the future. And there is a well-established formula to score how well a distribution fits a given value. So when we know the true value, we will score your value. This is how we will do. One thing I think I went a bit fast to mention is, of course, when we will fit the model to the ARMA noise, I explained a bit informally that I tried those values here. So here I said, I see something at 16, so I keep 16. But here, what of course we will do is apply the AKI or an information criteria, for example, AKI information criteria, to find the best P here. We know that if we take a P too large, we will be doing overfitting. So you can always fit an ARMA model with 1 million coefficients and will fit exactly your noise trace. But of course, as we know from what we saw also from machine learning, we don't want to do this. The AKI information criteria requires which information? If you have to code that concretely. Number of parameters and the likelihood. Right. Fortunately, for a least square model, the likelihood is a function of the log of the estimated variance, sigma square. Right? So this is, once you do the least square, you have the likelihood for free. So of course, the MATLAB, and I guess the Python code, which is for that kind of thing usually copied from MATLAB, will return to you all the elements to compute the AKI information criteria if it doesn't do it already. So this is a natural thing we need to do here. I will mention a few other tricks. I mean, prediction, as you can imagine, is one of the major activities that humans like to do, because as humans we love to talk about things that don't exist. And I think I will, if you agree, I will use, because we don't have much to do, so I will use the break now to finish, and then we will finish much earlier. If that's okay with you. If anybody needs a break, we can do a break. That is long overdue, by the way. Can we continue? Is that fine? Or? Yeah. We will not do machine learning methods, but I'm looking forward to see some of them perhaps in the mini project. all of those things can be combined together. In particular, the filter the data, that's something that is always worth doing, whatever the method is at the end. What we will see is how to combine things like, for example, linear regression or any model fitting method with ARMA noise. So linear model fitting says I fit here, I'm just doing a linear one, but other models, other types of fitting, we say I explain the data by a model, that's parameter beta, plus noise here. If the noise is ID, Laplace or Gaussian, we know how to fit. We fit L2 or L1. But in general, it's very often noise is not ID. So one method is, of course, to combine the two. So you combine your model fitting or your machine learning method with something that says the noise, or the residual of whatever I obtain, is itself autocorrelated noise. So it's F, where F is an ARMA filter, with W, where W is some noise of some kind. And then how to fit that? Well, we know that if I know the filter F by applying the inverse filter, if it's an ARMA filter, the inverse is a well-behaved filter, I inverse filter the data, and then I do the fitting. So I can find the parameter beta if I know the filter. Conversely, if I know the parameter beta, I can find the filter because this is the ARMA fitting that I've discussed already that MATLAB does for you. So one method is to iterate between the two. I've separated the problem into I have to find an F, I have to find a beta. I know how to find F if I have beta. I know how to find beta if I have F. So the best thing to do is to iterate between the two. Not the best, but one of the classical ways to go at such hard problems is to iterate between the two. For example, you start by fitting this, assuming the noise is ID. Then you will re-estimate, then you estimate the noise, and then you estimate the F of the noise obtained from the first beta. And then once you have obtained F, you will re-estimate beta, and very often the method works well. That's one of the zillions of tricks you can use. A more important trick is what is called sparse models. Well, that's a constant problem in signal processing, in machine learning, also here. For example, my time series that I had before is periodic of period 16. There are ARMA models that are automatically of period 16 and that have very few parameters. They are called multiplicative or additive ARMA models, though they can be used here. Another one is called Holt-Winters model. So Holt-Winters are very, very simple models that allow for modeling three things. First, a trend. Second, seasonality. And that's it. The benefit of Holt-Winters, so they are ARMA models, but with very few parameters, 3 parameters, right? Alpha, beta, gamma, once you know the period. So having few parameters make it likely that we are going very far away from the overfitting problem, and also those parameters are very easy to obtain practically. So here I did it with the best models. So Roberts is another one that I won't discuss in detail. But with Roberts' model is a seasonal ARMA model, right? A seasonal model is one that factors in already in the ARMA modeling the fact that everything must be periodic. So it allows to have much fewer parameters here. You see that the fit here is extremely improved, at least at the beginning, by having a seasonal model. Right? It's quasi-perfect here, which of course is a small deviation. Here another take-home message is the ARMA model. So that's the one we obtained before, right, with the techniques here. So by those sparse modeling, here it's much sparser and quasi as good as this one, which is much more complicated. And if you want something really better, then using a seasonal model will usually give the best fit. Because it's sparse, because it has a structure that mimics some of the structure we know of the system, which is its periodicity. Of course, the whole trick of forecasting is if once you know other things, you try to capture them by a model that in its structure has those other things. That's next week of last week. Voilà. that's all we will do, at least for the theory part of forecasting. There is also a little homework on forecasting. I encourage you to do it before doing the lab, because the paper and pencil exercise is like a drilling of how to use filters on simple cases. In the lab, if you use filters, well, it's up to you. You can use any methods, but if you use filters, you will have to implement in MATLAB the things that we do manually in the paper and pencil exercise. So I encourage you to do them. Also, don't forget, the deadline for the mini project is on the 4th of April. Right? So far I have 2 groups of students who have manifested themselves. You can do it in groups of up to 2 people. But please speak to me if you're stuck. Otherwise, input something into Moodle by Thursday. Thank you.